Hello students, welcome to EPG Pathshala. I am Tanushree Shahadas Gupta, Professor and Associate Dean in S.N. Bose National Center for Basic Sciences in Kolkata. I belong to the Department of Condensed Matter Physics and Material Science. I am also the coordinator of the thematic unit of excellence on computational material science set up within S.N. Bose Center. In this lecture, we will discuss applications of Hartree and Hartree-Fock theories, which has been covered in two previous lectures. We will consider for this purpose the free electron gas model. Free electron gas is a collection of electrons moving in zero external field. Even if there may be source that should produce a constant potential so that the derivative is zero. Note that we will be considering interacting free electron gas as opposed to the non-interacting free electron gas, in which one neglects the electron-electron repulsion as done in Sommerfeld model. In interacting free electron gas, one takes into account the effect of electron-electron repulsion. Therefore, this needs the presence of a positively charged background for stabilization. This positive charge distribution, however, should be uniform so that it gives rise to a constant potential. This model is also popularly known as Jellium model. The modern-day density functional theory, to be discussed later, makes use of the properties of the homogeneous interacting electron gas, and thus it will be useful to have on hand some analytical results of Hartree and Hartree-Fock theories applied to this model. This is also a good model to describe alkali metals like sodium. As we will see, Hartree theory fails completely for the total energy, though it gives reasonable estimate of the Fermi energy for the free electron model. Hartree theory does not even provide binding. On the other hand, one gets a negative binding energy by Hartree-Fock theory. Hartree-Fock theory, on the other hand, gives the value of the density of states of the free electron model at Fermi level to be zero. This is a wrong result. It also fails in describing the magnetism. For example, for cesium, for which the free electron model is expected to be applicable, as we will see, Hartree-Fock predicts it should exhibit ferromagnetism. But this is not the case in reality. We will also discuss the exchange charge density in free electron model. Finally, we will discuss the concept of correlation energy, which mathematically can be defined as the total energy difference with the proper allowance for Coulomb interaction and that given by the Hartree-Fock. The former is also described as the exact total energy. Physically, each electron is affected by the motion of every other electron in the system. This is what is known as the correlation property. The electrons themselves, being interacting particles, experience the effects of this long-range interaction, since the motion of one affects the motion of each and every other one. This leads to the correlation aspect of the many-body wave function. While Hartree-Fock ignores completely the effect of correlation, it is taken into account in an average way in the density functional theory, which will be the topic of discussion later in this lecture series. We will now move on to the details of the mathematical steps that will be required in the application of Hartree and Hartree-Fock theory to the free electron model. The plan for today's lecture are the following. We'll start with the definition of free electron gas, which in our case is the interacting free electron gas. We'll then discuss the application of Hartree theory to the interacting free electron gas. We'll derive the expression for total energy of free electron gas in Hartree approximation. Following this, we'll discuss the application of Hartree-Fock theory to the interacting free electron gas. We'll derive again within the Hartree-Fock approximation the total energy of the free electron gas. We will discuss the shortcomings in Hartree-Fock theory of free electron gas. We'll then discuss the exchange charge density in free electron model. And finally, we'll introduce the concept of correlation energy. What is a free electron gas? Free electron gas is a collection of electrons moving in zero external field. Even if there may be source that should produce a constant potential so that the derivative is zero. We can have two different electron models. Firstly is the non-interacting free electron gas. In this model, one neglects the electron-electron repulsion, as is the case in Sommerfeld model. Another is the interacting free electron gas, which is of our interest. This model takes into account the effect of electron-electron repulsion. Therefore, this needs the presence of a positively charged background for stabilization. This distribution, however, of this positive charge should be uniform so that it gives rise to a constant potential. The density of positive charge for n electron system should be given by rho equal to Ne divided by V, where V is the volume of the system. Let us start with a typical example of sodium metal, where the free electron model is expected to be applicable. The electronic configuration of sodium atom is given by 1s2, 2s2, 2p6, 3s. The wave function is given by phi ak, that depends on the space coordinate r. Since it's an atom, let's start with this phi, which is given by these quantum numbers NLM, and then it has a radial part which is given by RNL, that depends only on the radial coordinate, times the spherical harmonics, which is given by this YLM. Now the spherically average charge density is given by rho NLM, which is taking into account this spherical symmetry, is integrated over the spherical part, which is given by d omega, and modulus square of phi NLM, which was a function of r vector to the power square, and 1 over 4 pi. And that is nothing but RNL square, which is given here, the radial part square. The spherically average density for electron in a shell designated by the quantum number n is then given by rho n, which is summation over Lm, with a coefficient alpha NLM times rho NLM, which is a function of r, where rho NLM is the number of electrons in the state phi NLM, which may be 0 or 1 or 2. Thus, we have the K shell where the density is given by rho 1, which is 2 times rho 100R. So, which is nothing but taking n equal to 1, L is equal to 0 and M is equal to 0, and there are 2 electrons in this 1s state. So, these will be 2 times R10 square. We then go to the next shell, which is the L shell. Then it is row 2, and this consists of 2 times row 200, which is basically L equal to 0, M equal to 0. That's the contribution from the S, and there are 2 electrons, so it's 2 times that. And then we have the contribution from row 210, row 211, and row 21 minus 1. So these are all the contributions from L equal to 1. For M equal to 0, M equal to 1, and M equal to minus 1. So these are the contribution from the p electron, and there are 6 number of p electrons. So the coefficient in front of all of these is 2. So this can be written as 2 times R20 square plus 6 times R21 square. Moving to the last shell, that's the 3s shell, the row 3 is then given by row 300, which is n equal to 0, L equal to 3, and M equal to 0. So for that, this is basically the contribution from 1 electron in the 3s shell, and this is given by R30 square. This is just the contribution of the S because the P's are all empty. So what it shows here is this spatial variation of rho r for different values of the principal quantum number in 1, 2, and 3. And this is just a schematic diagram. As far as the K and L shells are concerned, which is n equal to 1 and 2, so as you can see, so I have this one sodium atom and another sodium atom. These wave functions, or the charge densities, they don't penetrate in the charge cloud of the neighboring atom. The nearest neighbor sodium-sodium distance is 3.67 angstrom. However, for 3s wave function, this charge density is pretty extended, and it does become the part of the neighboring sodium site. So this electron, which is in the outermost shell, is loosely attached to the parent electron, and eventually it is detached and remains in the interatomic space, in the space between 2 sodium atoms. Thus, we can define 2 types of electrons. First is the core electrons, which in this example is n equal to 1 and n equal to 2. So these electrons together with nucleus forms the ion core. The second kind, the valence electron, which is in this case is this n equal to 3, this 3s electron. These electrons take part in the conduction forming free electron gas. For electrons forming free electron gas, that's the valence electron, one can write the corresponding Schrödinger equation, which is given by minus h cut square divided by 2m delta square plus Vr times psi r equal to epsilon psi r. Now the potential V has 2 parts. One is V1, another is V2, where the V1 is the potential due to ion core and V2 is the potential due to interaction with other electrons. The variation of V1, which is the potential due to ion core, between 2 sodium atom which is sitting at site A and site B, as will be next discussed at length in the next slide, this variation is shown here. So for R tending towards 0, when I am close to this ionic site of the sodium atom, this V1, which we call as a V10, is given by minus Z times A square divided by R, where Z is the atomic number. Now when the R is very large, is going to infinity, then the variation of this V10 is minus eta times E square by R, where this eta is the ionicity. This V10 is the ionic potential of the individual sodium atom, so the sodium atom which is either at site A or B. Now, as we have seen in the previous slide, which shows the distance dependence of this V10 for 2 neighboring sodium atoms at site A and B, the resultant potential, which is the combination of V10 at site A and site B, this V1, which is the resultant, is nearly flat in the region in between A and B, that's the two atom centers. The nearest neighbor distance is then larger than the extent of the individual ionic potential well, which is given by V10. In this case, the valence electron spends most of the time in the flat part of the potential V1. As a result, the free electron theory may be applied. This is the situation which is satisfied for alkali metals. Let us now move on to the discussion of application of Hartree theory to interacting free electron gas. The single particle equation in Hartree method is given by this following expression. So this is given by minus h cut square over 2m del square plus V1, which is from the ion core part, plus E square summation over J not equal to K modulus phi Aj square divided by R minus R prime integrated over dr prime times phi Ak equal to epsilon Ak phi Ak. Let us consider as starting wave function the free electron wave function, which is given by this following form: 1 divided by square root of omega, where omega is the volume, e to the power I k dot r, as is shown here. This gives the charge density rho r is equal to minus E times summation over J modulus phi Aj square is equal to minus E over omega, if you use this form, summation over J times 1, and since there are n number of electron, this would give minus n times E divided by omega. Thus the positive charge density, if you remember, which was given by plus Ne by omega, cancels exactly this negative charge density. The single particle state is then given by only the contribution from the first part, which is minus h cut square divided by 2m times del square times phi equal to E psi, and the solution is the free electron wave function which we started with. This gives rise to the following property, which is the density of state is the free electron density of state and with a square root energy dependence, as is shown here. The expression for the Fermi energy is given by h cut square divided by 2m times 3 pi square times n divided by omega to the power 2/3. And one can rewrite it in terms of Rs, where Rs is the radius of average volume available to each electron, which is given by the formula 4/3 pi Rs cube, that's the spherical volume available to each of the electron, times n by omega is equal to 1. From there, one can have an expression of Rs in terms of n by omega. For sodium metal, the value of this Rs, which depends on this density, which is given by n by omega, is 3.97 atomic unit. And putting that value here, one then gets the expression for the Fermi energy for sodium metal as 3.2 electron volt. This is in reasonable agreement with the experimental value, which is from 2.5 to 3 electron volt. The expression for total energy in Hartree approximation is given by this following expression, which has this three term. The first term being summation over I epsilon Ai, the second term being given by minus E square by 2 summation over Ij with I not equal to j integral modulus Aj square times modulus phi Ai square divided by R1 minus R2 integrated over R1 R2, and the last term, which is the contribution from the nuclear term, which is given by Z square times E square divided by capital RA minus capital RB, where capital R denotes the coordinates of this nuclei. For the free electron gas model, this gives rise to substituting the plane wave form for this phi. This gives rise to this following expression for these three different terms in the total energy. In this above, we assume that there are equal number of spin up and spin down states, and in the second term in the summation we don't have any longer this hash sign, which actually means that I is not equal to j. This can be omitted since it is a large system of delocalized electrons. This gives rise to the expression for total energy as is given here. And after a few lines of mathematics, which is shown here because the second and the third term basically cancel each other as we have discussed already, and then putting the value of the summation over k by substituting it by the corresponding integral because k is a continuous variable, and then after a few lines with this including this expression for this Fermi energy, one can actually write it as 2.2 times Rs square and in unit of Rydberg. However, we find the sign of this is positive. So this is positive energy. Thus, one cannot get binding of the system because to get the binding, the total energy should be negative. The system is thus unstable. Therefore, Hartree theory fails for the total energy, though it gives reasonable estimate of the Fermi energy for the free electron model. We next discuss the application of HartreeFock theory to interacting free electron gas. The single particle equation in HartreeFock method is given by this following expression, which is minus h cut square by 2m del square plus V1, the contribution from the ionic term, plus the contribution, the Hartree contribution, which is square summation over j integral phi aj square divided by r minus r prime integrated over dr prime. And then the fourth term, which is basically the contribution from the exchange, which is given by minus a square summation over j, where the summation over j's are over the electrons having spin parallel to that of the I, and given by integral phi star aj times phi ai times phi aj divided by r minus r prime times phi ai, and the whole thing multiplied by phi ai equal to epsilon ai phi ai. As in the case of the Hartree theory, we take the plane wave as the starting functions for phi. So what are the initial guess for phi? We started with the plane wave. And as we have seen before while discussing the application of Hartree theory to the plane wave case, we also find in this case similarly the second and the third term they cancel because we have this positive background and this negative background of equal density. And the fourth term, which is given here, is given by this following expression where instead of phi's we have now used their plane wave form. And after a few lines of mathematics, this is given by minus 4 pi e square divided by omega equal to summation over k prime 1 over k minus k prime modulus square. We then have this equation, the Schrödinger equation, which is given by minus h cut square 2m delta square plus the contribution from the exchange part, which we call as Vx, times phi k equal to epsilon k phi k. This we can write as minus h cut square divided by 2m del square times phi k is equal to epsilon k, taking this Vx in the right hand side minus Vx times phi k. This we can redefine as a new energy which is given by epsilon prime. Solution of this above is again a plane wave but with a shifted energy which is given by epsilon k equal to epsilon prime k plus Vxk. And we know the form of this epsilon prime because which is the plane wave solution, which is given by h cut square K square divided by 2m minus now the form, substituting for the form of the exchange which was derived a slide back, minus 4 pi square divided by omega summation over k prime 1 over modulus k minus k prime square. We can work out the following expression for Vx, which we start with this expression which was derived a slide back, and then we replace this summation over k prime by the corresponding integration which is given by omega over 4 pi cube integral dk prime, and then we can basically have the integration over the radial part of the k and its angular part, the theta and the phi, and then after a few lines of mathematics one can actually derive this expression of Vx in terms of k and kf, the kf being the corresponding Fermi wave vector. Note this second term shown here, it diverges by ordinary calculation. One needs to take kf outside and then expand in this logarithmic term. We thus have the final expression for this energy dispersion, epsilon of k, which is the contribution from this epsilon prime, that's h cut square, k square by 2m, and then the contribution of Vx, which is given here. We note that the expression in previous slide is a spherically symmetric function containing only the magnitude of k. This gives the expression for k equal to 0, which we call as epsilon of 0, minus 2kf square by pi. And the expression of this energy setting k equal to kf, that's at Fermi wave vector, is given by h cut square kf square by 2m minus kf square by pi. The difference of these two gives the estimate of the bandwidth. This gives, applying this to the case of the sodium metal, this gives too large a bandwidth of sodium 3s, which turns out to be 7.2 eV. We need to remember that only correlation between parallel spin electron has been taken into account within the HartreeFock theory. The expression for total energy in HartreeFock approximation, if you remember, is given by these following four terms, which consist of summation over epsilon ai minus half of summation over ij, ai aj times v ai aj minus ai aj v aj ai, and the contribution from the nuclear or the ionic interaction. So these three terms rather, were already there in the Hartree theory, and the new contribution is this one. For the free electron problem, the last, that's the fourth term, cancels the second term as we have seen in case of the Hartree theory. Thus, we have the contribution from the first and the third term. And this is given by summation over epsilon ai, the first term, and then the contribution which is plus square by 2 and now written in the wave function form. So these can be written as twice because summing over both up and down spin, summation over k, h cut square, k square by 2m plus summation over k, Vx, that's the exchange potential. In case of Hartree theory, we had only the first term in the previous expression. Now the average energy in the HartreeFock is thus given by the contribution that we have come across already in the Hartree theory, which is given by 2.21 divided by Rs square. But now we also have another contribution, and which is of negative sign, it's 0.916 divided by Rs. So I have a contribution which is positive and a contribution which is a negative. Thus, there is a possibility of getting a net negative energy, and thus the binding depending on the value of the Rs. For example, for alkali metal, the Rs lies between 3 atomic unit and 6 atomic unit, and one gets a negative binding energy by HartreeFock theory. In particular, for sodium metal, Rs is 3.97 atomic unit. This gives the value of average energy as minus 0.0905 Rydberg, while the experiment estimate is minus 0.081 Rydberg, not to a bad agreement with the experimental estimate. This is the list of different metals and the corresponding Rs values. As you can see, since this Rs is lying in between 3 and 6, we get binding in all the cases. Let us now discuss the shortcomings in the HartreeFock theory of free electron gas. The first issue to be discussed is magnetism. So far, we have assumed a non-spin polarized situation with equal number of up and down spins. If we consider the situation with all electrons having parallel spin, this leads to a ferromagnetic solution. Whether the ferromagnetic solution will be stable or not depends on the energy of the ferromagnetic solution, whether it's lower than that of the non-spin polarized situation with equal number of up and down spin. This condition can be expressed in the following way. If you remember, this is the expression we derived for this energy, assuming equal number of up and down spin. If we assume all spins to be up, then this is the expression we get. So for ferromagnetism, which is the situation shown in the left-hand side, will be stable if this energy in the left-hand side is lower than the energy in the right-hand side. And this condition holds good only when the Rs is greater than or equal to 5.46 atomic unit. You can just derive it very easily from the above inequality. The cesium, which has a Rs value of 5.67 atomic unit, as was shown in the table in the previous slide, must exhibit ferromagnetism. But in reality, this is not the case. Therefore, the HartreeFock, as applied to the free electron gas case, will fail to explain the magnetic behavior. The second issue is the density of states. HartreeFock gives the value of the density of states of the free electron model at the Fermi level to be 0, while as discussed before, a non-zero value is obtained in case of the Hartree theory. The experiment is in agreement with Hartree result and is in disagreement with the HartreeFock result. Let us now discuss the exchange charge density in the free electron model. Total exchange charge around an electron is of magnitude plus c, and the charge should fall off very sharply as we move away from the electron. Exchange charge density at a point R2 due to electron at a point R1 in a state which is phi ai is given by this following expression, as you know from the previous discussion. It is given by E summation over J, where J are over the states or the electrons having spin parallel to that of the electron in the state AI. And then we have this phi star Aj times phi AI times phi Aj divided by phi AI. For the free electron model, for which the plane wave states are the solutions, and assuming the number of spin up and spin down electrons to be same, we get the following expression because we have to use this e to the power ik dot r for all the phi's. And a few lines of mathematics basically gives us this following expression, which is shown here. Expanding the above for small value of R1 minus R2 and taking the limit that modulus R1 minus R2 tending to 0, we get this following expression, which is nothing but Ne divided by 2 omega. The above exchange charge density is given by where we have this exchange charge density rho of x, and at value R1 and R2, this will be given by 1 over n by 2 summation, because we have equal number of up and down spin, summing over k, where the summation goes until kf, and this can be written in this following way, where this xi is nothing but kf times modulus R1 minus R2, which we can also write as R12, therefore it's kf times R12. The properties of the average exchange charge density are the following. Firstly, it is a real quantity. It is symmetric about the position R1. If we interchange R1 and R2, it remains invariable. And we have, when R1 is equal to R2, this modulus R1 minus R2 tending towards 0, as we have shown before, it is given by Ne divided by 2 omega. If we have this R12, which is R1 minus R2, at a value of Rs, this is already 0.42 times Ne divided by 2 omega. If we make this distance 2 times Rs, this is 2 into 10 to the power minus 2 times Ne divided by 2 omega. The exchange charge density, as you can see, thus falls off very, very sharply. The net parallel electron density is given by the contribution from this uniform background, which is minus Ne divided by 2 omega, plus the contribution from the exchange, which is given by epsilon x, that depends on this separation between R1 and R2, that's R12. So one can write it at minus Ne divided by 2 omega times f, and which is a function of xi. Xi was defined a slide ago. At xi equal to 0, that's when the R12 tends to 0, phi of xi will be 0. And at xi infinity, that's an asymptotic limit, f of xi will be 1. There is therefore the cancellation of the real charge by the exchange charge, forming a depletion of charge known as Fermi hole or the exchange hole. We next discuss the concept of correlation energy. Correlation energy is the difference between the total energy obtained with proper allowance for Coulomb interactions and the Hartree-Fock total energy. In Hartree-Fock theory, the effect of correlation is introduced by assuming antisymmetric nature of wave function, but not the actual Coulomb interaction leading to the difference. Within the free electron model, which as we discussed, is applicable for alkali metals, the expression for correlation energy, considering an interpolation between the low density and high density limit, is given by this following expression, which is minus 0.88 times rho to the power 1/3 divided by 0.62 plus 7.8 times rho to the power 1/3. This is also known as the famous 1/3 law. To summarize, in this lecture, we discussed the application of Hartree and Hartree-Fock method to interacting free electron gas problem. We compared the advantages and disadvantages of the Hartree and Hartree-Fock method in the context of free electron gas. Finally, we discussed the concept of correlation energy. Thank you for your attention.